to reliability. So let's talk about lubricants and lubrication as a pathway to machine reliability. And if it's possible, if you're able to minimize your window, that'd be good just to make it a little bit bigger on screen. So lubricants and lubrication as a pathway to reliability. So, sorry about that. Here we go. So if you look at data that comes from a couple of... Oops, I've got some feedback here. I think you might have to put yourself on mute. So there are a couple of studies that have been done across the industry by various different original equipment manufacturers. So if you look at data that comes out of Emerson, as an example, they talk about what percentage, they look at bearing failures and then they assess. Oh, thanks, that's fantastic. And they assess what the cause is. And you've got, the top causes of bearing failure for Emerson are incorrect lubricant choice, aged lubricant, insufficient lubricant, and solid contamination. Now, solid contamination, how does the solid contaminant get to the bearing? Right? It gets there via the lubricant. So that's also a lubricant-related failure. So everything that I've kind of put in that gold color is related in some way to lubricants. Same thing with Cummins on engine bearings. You look at lubricant failures, contamination failures. Again, contamination gets there because of the lubricant. And then surface reaction. What is a surface reaction failure? That's just another fancy word for a corrosive failure, right? And how does corrosion happen? Well, the lubricant is designed to protect against corrosion. So that is also affecting machine reliability. The challenge that we have, right, is twofold. I think most professionals that are in the industry understand the importance of lubrication to reliability. So here's an example, right? Reliability Web, if you're familiar with that website, they ran a survey a number of years ago, and they said, how would you describe the importance of precision lubrication? And overwhelmingly, the respondents said it's critical to our machine reliability. Basically, without lubricant, stuff breaks down very, very quickly. If you've ever run your engine dry in your car, you'll know how true that is and how fast failure can occur. But simultaneously, even though 80% of respondents said it was critically important, when you then flip the question and say, well, how many of you are not even at best practice? How many of you are considered close to best practice? 70% say, no, we're not there. So there's a huge gap. We know that lubricants are extremely important to machine reliability, and yet the vast majority of industry does not believe that they are achieving that sort of best practice. So for engineers like yourselves and like myself, that's a huge opportunity gap, right? There's vast opportunity for us to improve. So what are the kinds of things that I see in the field where we can improve, right? So one example would be over lubrication. So a lot of times we have a tendency to believe that under lubrication is a severe issue, and it is, right? So if we forget to re-grease a bearing and we allow it to run dry, or if we commission, let's say, for example, an electric motor without greasing it, that is also going to cause a catastrophic failure. But maybe what's underappreciated is the impact of over lubrication, right? If we pump too much grease into a bearing, we can cause increased temperatures. We can cause the rolling elements in either ball or roller bearings to skid, right? And that in turn is going to generate more wear and more temperature, right? And eventually we get more failure. Other issues that I see in the field, right? This would be an example. It's very common to see these kinds of units in the field, which are what we call single point lubricators or automatic lubricators. And the advantage of these is that they have this kind of set and forget principle, right? You can install them and then forget about them for a little while. Unfortunately, people focus on the forget bit, right? So they set them up and then they forget them and then they never really look at them ever again. And that leads to failures. As an example, right? So on the right, we have an automatic lubricator that is clearly over lubricating the bearing, and now we have grease that's spilling out. In some cases, for example, we have long lines from the single point lubricator to the point that needs to be lubricated. Well, they're often not rated for that sort of back pressure, right? And so what you often find is that the bearing will actually be receiving zero grease volume, and that's a problem. Other very basic issues that I see in the field, right, will be issues of procurement. So here's an example. This is almost like one of those spot the difference type of puzzles that you had when you were a kid, right? Have you noticed that one of those grease cartridges is quite different from the others? So if you actually notice, the one that is second from the left is a different type of grease. All the others are Shell Gaddis S2 V220 NLGI2. That one is Shell Gaddis S3 T100 NLGI2. So it's a different thickener type and it's a different base oil viscosity. So a vastly different product. And it's so easy for us to make those very, very simple errors. So a lot of best lubrication practice, you might seem simple, but a lot of it is just down to like generally good housekeeping, very good and robust procedures, and having a really good training program where you can teach the people the importance of lubrication. Something else, right, that I see would be poor storage practices and poor contamination control, right? So I see, often in storage areas, you'll see old drums that have been clearly sitting there for 5 to 10 years, right? Not in use. Here is an example in this particular video, right? If it'll play properly. So this, you can see those bubbles that are actually coming out of the drum. So this is where standing water has been sitting on top of the oil drum. And one thing that's underappreciated is that drums actually breathe. They're not completely airtight. And as that air is escaping, it's actually allowing water to go into the drum. And thus we are contaminating a perfectly new barrel of oil even before we ever use it, right? So ultimately what we went to get to when we're talking about best practice is we want to move into a paradigm where we consider lubricants to be assets themselves, right? So you might have heard the term, I will treat my lubricants as assets. You might think, well, what does that exactly mean? And it's a bit of a change in mindset, because when we talk about lubricant, we tend to think of the product. We tend to think of the turbine oil, hydraulic oil, gear oil, grease, right? It's the product. But in fact, lubricant is 3 separate but related disciplines, right? So there's the lubricant, there's the use of that lubricant, and then there's the analysis of that lubricant, right? And you can think of these as being lubricants, lubrication, and lubricant analysis, right? So 3 different things. And that's very analogous to the way that we would treat assets in the field. So you would have a machine, right, which you then operate and maintain, and you collect data on the operations and maintenance and reliability of that machine. So you can see very clear parallels. In the same way that we talk about a machine, that is the asset, we can talk about a lubricant as the asset. Moving over to the next column, we have the way that we operate and maintain that machine. Well, lubrication is the act of operating and maintaining the lubricant. And finally, on the third column, we collect data about the way that our machine is operating so that we can optimize it, and so that we can optimize and make our maintenance program a precise maintenance program. Well, in a similar way, we are going to collect data on the lubricant by using used oil analysis, right? Now, what's cool about lubricants and what makes it very unique among the condition monitoring disciplines is that we get to play jump rope with this line, because lubrication is also the act of operating and maintaining the machine as well. It's an input to that machine. And lubricant analysis can also uncover information which is directly tied to the performance of that machine as well. So not only can it tell us information about the lubricant, but it can also tell us information about the machine. And so that's why we want to get ourselves into this mode of thinking of lubricants like assets. Helpfully, the International Council of Machinery Lubrications, that's ICML, have come up with a standard, ICML 55, which basically takes the asset management principles that you might have heard of from ISO 55000 and says, how do we make that real, right? How do we make it real for the lubricants industry? I've also broken it down, right? So, just to go back to ICML, there are 13 different elements in these documents, and they're quite large. You can purchase them, and they're sort of 250, 300 pages each. And they're quite dense, but they're full of gold nuggets of best practice. If that is a little too in depth, I've kind of condensed it down to 6 core principles, which are select, detect, inspect, protect, connect, and reflect. So select is all about lubricant selection, right? It's about machine selection. Detect is about how do we do condition monitoring? How are we detecting early signs of lubricant degradation or machine degradation? Inspect is how are we doing our daily lube routes? How are we doing daily inspections on the lubricant? How are we checking, for example, oil levels, whether we need top-up volume? Is there any increasing levels of foam or water in the sight glass? Protect is all about protecting the environment as well as protecting our people. Connect is how are we connecting our people with best practice around the world? How are we training them? And then reflect is all about measuring our performance and improving our KPIs. Now, if you're interested, that QR code there will actually take you to like a sort of like an assessment, and you can basically, in about 20 minutes or so, kind of evaluate how well is your site doing against these metrics, right? And if you need any pointers, just let me know. All right. That then takes us to a pretty foundational concept, right, within reliability, which is called the PF curve. Now, I understand there's quite a few reliability engineers or budding reliability engineers on the call. So you're probably pretty familiar with this concept, the idea that machines have a certain amount of usefulness. Let's say, for example, an electric motor has a certain amount of power output, but then there's some kind of problem event. That problem event could be anything. It could be a top up with the wrong oil. It could be completely unrelated to oil. It could be that a bearing has been installed incorrectly. Maybe someone ran into it with a forklift and caused an imbalance. Whatever it is, after that point, the performance degrades until such point as we have failure. And condition monitoring, which is our thermography, it's our vibration analysis, it's our oil analysis, it's our ultrasound, all of that is an effort to try and detect signs of dysfunction before that catastrophic failure occurs. Now, where we don't want to be is we don't want to be in what we call this reactive domain, where we're constantly doing what is called reactive maintenance, which is I just let something fail and then I just replace the component. So in the oil world, that would be like, I don't know, basically, letting something run to failure consistently. The second kind of maintenance that we have is what you might term, let's say, preventative maintenance. Now, in preventative maintenance, we're doing fixed intervals. So in the same way that you might change the oil on your car every 10,000 kilometers, right? Maybe we overhaul a gearbox once every 5 years, or we do an engine overhaul every 20,000 hours or something like that. Right? So that's called preventative maintenance. Then you've got predictive, which is all about using our condition monitoring tools that are available to us. And finally, we have proactive. And proactive is probably the one that's less intuitive, because proactive is about fixing the root cause events before they ever occur. And it almost doesn't make sense to be able to fix something before it happens. So what do I mean by this? We often give the analogy that oil is like the blood of the asset. And so blood is to people what oil is to machines. And so what does it mean? I should just caution, this is not medical advice, but what does it mean to be proactive when it comes to blood and your heart health? Right? We know that the root cause of most heart disease is either genetic, which we can't do anything about, or it's down to diet and exercise. So it's lifestyle factors. So a proactive measure would be eating a good diet. Right? Then we have predictive. Predictive is we are going to fix the problem when we sense the problem. So maybe I do blood work. I go off to the doctor and I get my blood checked every now and then, and they test for things like blood sugars and cholesterols. And if I see signs of dysfunction, then maybe I act and I do something, make an adjustment to my lifestyle, or maybe I'm prescribed some kind of drug. Preventative would be, hey, what we're going to do is we're going to open ourselves up and do open heart surgery once every 3 years and get the doctor to clean out my arteries to make sure that they're nice and clean. Now, the obvious problem with this, right, is that you introduce risk. If I'm going for open heart surgery every 3 years, there's a good chance that I pick up an infection. There's a good chance that something goes wrong during the operation. And that's why, let's say, for example, when you see a mine site that is changing its oil every 6 months, we want to question ourselves and say, is there an opportunity to extend out that oil drain? Because every time we open up the gearbox, we are inviting contamination to come into the gearbox. And so avoidance of that is critical. And finally, in the heart analogy, we would just try and restart the heart, which is obviously not ideal. All right. So this is what it looks like for all of the oil. And yeah. So let me move on a little bit and talk about lubricant application. Right. So we're starting to get a little bit more practical, right? So in the actual use of lubricants. Now, lubricant application is done in a number of different ways. So, for most bulk oil systems, whether it's a gearbox or hydraulic pack, we are simply topping up with lubricants. So where lubricant application becomes really important is when we have systems. Let's say, for example, in open gear lubes, we have spray bar systems, or we are regreasing manually, right, with a grease gun. And these are probably the two most common types of grease gun that you'll see out in the field. So there's manual style grease guns, right, which you often see. And then we also have the battery powered or automated grease guns. And something to just caution people on with this. Number one is, how do we know what the correct volume of grease is that we're supposed to be using? It's very difficult to know that. There are a number of different ways that we can calculate. So if you go onto the internet, there will be a SKF calculator, an NSK calculator. There's something called the Trabon lubricant method. There's a whole bunch of different ways that we can calculate the correct amount of grease. But then we have to know, is our technician out there dispensing the correct amount of grease? That's a whole nother question. So we have to define our procedures with a lot of precision, right? The other issue with these manual grease guns is the amount of pressure that they can generate. So it may be underappreciated, but a lever style grease gun can generate in some cases up to 15,000 psi, right? So in many ways, we should be treating them as high pressure hydraulic equipment. If you go onto site and you were to talk about something which can pressurize itself to 15,000 psi, we would generally put all sorts of safety controls around it. And yet, with a manual grease gun, we don't. We believe that they are safe, and that's just simply not true. In some ways, what is even more dangerous is these battery-operated ones, because at least with a lever-style grease gun, if you start to encounter some resistance or some back pressure, then you feel it. You feel it in the grease gun. Whereas with these battery-operated systems, you're basically just holding onto a trigger. You never get that physical feedback, and it is very likely that you're going to do damage, if not to a person, right, with the hose blowout, then certainly to a machine. Because, one thing that I always ask is, do you know of a bearing seal that is rated to 10 or 15,000 psi? It's very, very, very rare. And so most likely when we are re-greasing, that grease is completely blowing past the seals. Right. So just in terms of manual best practices, again, a lot of this stuff seems really simple, but the basics are just not being done in industry. So it's, are we checking the volumes, right? Both that the grease gun is dispensing, but also that it is the correct volume is defined in the work instructions and has been calculated. Are we doing things like depressurizing the grease gun afterwards? So all of these things are contributing to potential machine failures. And the other thing that we need to ask ourselves is why we are re-greasing in the first place. Because in some cases, we are re-greasing to optimize the amount of grease or the amount of friction that's in the bearing. In some cases, we are looking to purge contaminants. In some cases, we are using grease as a seal, as in the case of labyrinth seals. Right. So we need to always ask ourselves, why are we re-greasing in the first place? Right. And we don't want to just pump, untold volumes of grease, because that could do more damage than good. And remember that there are consequences to over-greasing. We generate more heat. We generate more friction. We generate more wear. And these are all very similar circumstances to what happens when we undergrease. So if that is the case, how do we correctly calculate what amount of grease should go into the bearing, right? This is really important. As engineers, we should be able to define what the answer is. And yet, if you actually go through, and this was done, it was an LGI paper that was published in 2024. If you actually look at the different calculators right? And you input the same numbers, so the same bearing specifications, same speed, same operating conditions, and you put them next to each other, you actually get vastly different results, which suggests that most of the calculators are actually incorrect, right? And that should put us in a bit of a bind as engineers, because we're always seeking what should be the correct answer. So how do you correctly grease a bearing? Okay, this is when we start to talk about one of those condition monitoring disciplines and the overlap that it has with lubrication, and this is ultrasound, right? So one thing that people may not be aware of is that you can use ultrasound technologies to actually basically listen to the bearing. Once upon a time, some of the old school technicians will have used, you might have seen them use basically a screwdriver on the side of their head, and then they lean over and they listen to the bearing. This is basically a more sophisticated version of that. And what you can see here, right, is if I can sort of point to it on the screen here, right, here, what we are showing is this is the ideal case, right? We're not over lubricated, we're not under lubricated, we're in this sort of Goldilocks zone in the middle. And what that is suggesting is that we have correctly calculated the correct amount of grease. However, let's say, for example, it was the work instructions were, well, let's do 4 shots of grease each day, for argument's sake. How do we know what the current state of the bearing is? Because even if that number is correct, if the bearing is already over lubricated, we're just going to keep it in that over lubricated zone. If it's under lubricated, we're going to keep it in that under lubricated zone. That's not ideal, right? What ultrasound does is it gives us feedback, right? It enables us to look at, hey, this is what the sound signature would look like if it was over lubricated. Down here, this is what the sound signature would look like if it was under lubricated. And as we lubricate, we can bring it into the ideal state, right? So again, we're starting to bring in some of these condition monitoring tools. Okay. And so this is what it looks like to have a bearing that is under lubricated and then receives the correct amount of lubricant. And you can see that sound signature collapse, right? There's actually a sound file that's here, which I don't think I'll play for you. And this is and on the right is what happens if you would continue to pump grease and put it into an over lubricated state, right? So bad things also happen there. Okay, something else to talk about would be cleanliness. So, I mentioned at the very top of this that storage and handling is something that has been done very poorly on most sites. So, what is the importance of contamination control? This is a really interesting case study that was done by Nippon Steel. Right, the blue line is the number of pump failures that they have each year. The red line is the number of filters that they installed on site each year, right? And what you can see is that they're inversely correlated. So basically, what it's saying is the more filtration that we install on site, the cleaner our oil gets, the fewer pump failures that we have. So there's a very, very clear line between cleanliness of oil and machine reliability. In fact, we have these things called life extension tables. Let's say, for example, we can look at the effect of water on bearing reliability or bearing life remaining. And what you find is, look at what that dotted line is showing us, right? Right. This here is a line which is less than basically 0.1% of water in the oil. So incredibly small volumes of oil are having a massive effect on the potential bearing life, right? We also have these things called life extension tables, right? So here, for example, we can talk about cleanliness codes. I won't go into detail about what the cleanliness codes are now. That's probably for another lesson. But basically, if we can clean the oil from this number to this number, it suggests that, as an example, right, for gears, we can get a 3x extension of asset life. And for hydraulics, we could get a 7x extension in asset life. And there are similar published numbers for rolling element as well as plain bearings. So why is it that these contaminants are having such a massive effect on the life of our assets? Well, it's because of the clearances that are involved. Some people may not appreciate this, but if you have a rolling element that is spinning, let's say, for example, it's in an electric motor, as it spins, which it's doing so very, very fast, right? It is being supported by an incredibly thin film of lubricant. That, in the case of rolling element bearings, we would say that the lubricant film is probably in the order of about 1 to 2 microns. Now, that's incredibly small. That is completely invisible to the human eye. It's smaller than a blood cell, right? So actually, if you were to take a section of the bearing and you were somehow able to look at it while it was spinning, it would look like there is no lubricant film, which means that if a contaminant is able to get wedged between the roller and the outer race, it's going to cause a lot of damage. Number one, because there's the potential for abrasive wear. So it's almost like, let's say, for example, abrading the surface. It's almost like having sandpaper or something like that. But the other thing that it does is it increases the local surface stress at the metals, which is going to, and you'd probably be learning in university, that's causing cracks to grow and eventually propagate to the surface. So as a result, contaminants are incredibly, incredibly damaging to machinery. And we have to be really careful about how we store and handle our lubricants for maximum oil cleanliness. So as an example, I talked about the fact that drums breathe. Yeah, they're not airtight. And so what happens is basically during the day, it's not actually the oil that expands. I'm just kind of illustrating it that way. It's actually the air that is trying to expand and it is able to escape during the middle of the day. And at night, when things cool down, it's going to want to draw air back in. And as it draws humid air, right, that's one of the ways that water can get into perfectly new oil. So we do have, for example, best practices around drum storage and how you should store drums, right, generally on their side. Other things that we can do, we can employ things like desiccant breathers. So if you've ever, in food packets, there's those little packets of desiccant which help keep things dry. You might even use it in your closet, for example, to stop the buildup of mold. Then we can use these very successfully, right? So these desiccant breathers, right? Oops, hang on, let me go back to the presentation here. They seem very simple. So all the blue material on the inside of this is desiccant. But what that's doing is it is drying the air as it makes its way into a gearbox or into a hydraulic reservoir to ensure that it is free of water. And we'll have air filters in there to make sure that we're capturing that particulate and that contaminant as well, right? So all of these things are adding up to the picture of reliability that we want to build. All right, so now let's talk about another condition monitoring discipline, which is the used lubricant analysis or used oil analysis. And if we had to talk about it in the same way that we talk about the P to F curve, right? So used oil analysis, we get both proactive and predictive information. So predictive is talking about the wear of the machine. Proactive is talking about how is the oil degrading in service, as well as, the level of contamination that we have. And oil analysis is incredibly important. You want to use it in conjunction with some of the other condition monitoring disciplines. It's best used as part of a program where we use it with thermography, with ultrasound, with vibration analysis, with something like motion amplification. As you start to piece all of these things together, you get a much better feel for the current condition of the asset. And it's because each of those technologies kind of shines at highlighting a different failure mode. So a couple of the things which oil analysis does extremely well is the very, very beginnings of wear, right? So you'll be able to detect that inside of the oil extremely early, potentially a lot earlier than you'll see, for example, heat generation through thermography or some sound signatures through either ultrasound or vibration. So it's able to detect that. The other thing that it's able to do is detect degradation of the oil, which is something that the other condition monitoring disciplines just can't do, right? So that's the advantage that we have when we're playing with oil analysis. Now, whenever you get an oil report, they're all formatted slightly differently, but they basically contain the same information, right? They contain information about the sample. They contain information about the lubricant condition, the wear metals, the contaminants, as well as the additives. Now, we're not going to go into incredible detail on all of the different test methods and all that sort of stuff. Suffice to say, most people are taking these reports and then they're filing them away to never be seen again. And that's a real shame because there's valuable, rich data in that report. So we need to apply our own knowledge and our own interpretation to this report because, right, how does the lab know what's an additive or what's a contaminant or what's a wear metal? They don't. They're using a rule of thumb that if they see iron, it's most likely going to be a wear metal. But if you work at an iron ore site, right, iron dust is constantly blowing in. So it might not be a contaminant. It might not be a wear metal. It could be a contaminant. In a similar way, if we see aluminium, but we're at an aluminium smelter, right, alumina dust, right, is very abrasive, and so we want to keep a track of it. But also, right, it's a contaminant. So again, we're having to apply our own knowledge and our own interpretation to these reports. And ultimately, what we're looking for is we're looking for trends. We want to be able to spot things before they become a problem. So, for example, we expect, in the case of the graph on the left, we expect viscosity to slowly trend up over time. That's what we expect. If we see a drastic decrease, as in the second one, then it's very likely that we've topped up with the wrong oil. And that happens all the time. That's why we encourage really good labeling practices. Alternatively, if we see a change in that viscosity increase, right? So a change in the rate of change, right? That could be possibly contaminants that are coming in. So we always want to look at these patterns. When we look at wear, we want to look at multiple patterns of information, right? Because the way that two different sets of data trend might tell us a little bit more about the asset, right? Now, I am conscious that I am kind of running basically to the 40 minutes now, and I want to allow plenty of time for questions. So I'll just stop it there, right? I know we covered a lot of ground in terms of the basics of lubrication, best practices in the field, oil analysis, contamination control, storage and handling. But these are all really important foundational building blocks for a really good reliability program. So we need to have all of the basics done right. And then lubricants and lubrication can basically act as they were intended. So, really appreciate your attention over the last 40 minutes or so. And now, if people have questions, make sure you chuck them in the chat. Maybe as people are firing up the questions, I can talk a little bit about sort of career. So Essa had asked me to maybe talk, a little bit about sort of career prospects and that sort of stuff in the lubricants industry. I would describe a career in the lubricants industry as being very, very fulfilling, right? I don't know if anyone has seen the American TV show Mike Rowe's Dirty Jobs, right? So it's basically this guy who he goes and he visits all sorts of different job roles, sewerage treatment plants, landfills, construction jobs, mining jobs. So, heavy industry, basically. And he takes a peek into what it takes for people to work in these jobs. That's basically what my job is like every day, because lubricants touches so many different aspects of our economy. It touches transport, aviation, marine, agriculture, food manufacturing, power, oil and gas, mining, metals processing, right? All of these things require lubricants. Yep. And so as a result, you get involved in some really, really interesting projects because everything is related to lubricants. So from that perspective, I found it to be a very, very fulfilling career. What are the job prospects like, though? Right? It was probably another question. I'd say the job prospects are pretty good, right? Because we have an aging workforce. And basically, as the very experienced people are starting to approach retirement age, there are very few people to replace them. And yet, lubricant volume is going up. Let's say, for example, in the next 10 years, lubricant volume starts to decrease because everyone transitions to electric vehicles. I think even in that case, from a personal career standpoint, so many people are leaving the industry that basically the lubricant volume per person is going to continue to increase. So I do think career prospects are pretty good. Now let's see. I've got a question here. Is it only one? Oh, I think that should be ICP. Is it only ICP that we can use to determine wear metals? Great question. Right. So let's go back to the presentation here for a second. So wear metals, the most common wear metal is going to be iron, and that's determined by ICP. There's a couple of different versions of ICP. There's ICP AES, which is atomic emission spectroscopy, and RDE, which is rotating disc electrode. You could also detect wear metals through XRF, which is X-ray fluorescence, but that test is probably a little bit more rare when it comes to the used oil analysis labs, and it has some restrictions in that it can only detect heavier metals, so basically from magnesium down on the periodic table, right? So that is, there are a couple of variations there. The other one is the PQ index, right? So here, that's the red line. Right, so the PQ index is basically a Hall effect sensor where they put the sample inside of a magnetic field and they look at the deflection of the magnetic field, and it can give you an overall impression of the amount of what we would call magnetic or ferrous content in the sample. So here on the bottom right, you can see, hey, is there a situation in which you get increasing levels of ICP iron, but the PQ index stays low? Yeah, that would most likely be rust, because iron oxide isn't magnetic in the same way that raw iron is. So hopefully that answers Davis's question. All right. Are there any other questions? Just trying to monitor the chat here. Maybe other things about the career while people are thinking of some questions. What are some of the best pathways? So historically, the way to sort of get into the lubricants industry historically was to kind of get a job at one of the majors, Mobil, Castrol, Shell, Total. That increasingly has become a difficult pathway because those companies are hiring a lot less. So most likely you're going to be going to one of their major distributors. They still have the resources to be able to train you, and then maybe you can further your career from that point. Oh, hang on. Patrick has a question. How does the breather work, especially in a lube room or system? Good question. All right. So how does the breather work? Maybe I can go to this. Okay. So you can see here, right up on the top right. So hopefully I'm highlighting that with my cursor there. That's the desiccant breather. So the idea is that humid air, right, is going to come in through the breather. The desiccant is then going to absorb as much of the moisture from the air as possible, and therefore dry, filtered air is then going to make its way into the reservoir, right? That is the primary mechanism by which the air is dried and filtered. However, there is a kind of a second order effect, which is that even if there is no airflow, right, in a similar way, if you leave a bag of desiccant in the corner of your bathroom, right, it will still reduce the amount of humidity that is totally in the bathroom. I believe it's called Hayes law, right? So basically, what will happen is it will locally absorb some moisture from the air around it, and that's going to cause an imbalance in the amount of moisture that's in the room. And so slowly the moisture will start getting drawn toward that desiccant breather. So even if there is no airflow, simply by virtue of having some desiccant that is connected to the air in the reservoir, it will slowly dry the water that is in the air over time, right? And as a result, you'll get less water getting into the oil. So again, as more questions come in, I can talk a little bit more about the career stuff. So like I said, you're probably looking to go to a distributor, right? The distributors are getting larger and larger now. So you're not directly working for Shell. You're probably working for one of Shell's distributors. I believe in Africa, that might be Vivo. or VTOL, who has the primary shell distribution. There are still some companies that do direct business. So, for example, where I live, Castrol in Australia still continues to do direct business, as does Fuchs. But in an ideal world, you want to find yourself a good business that has access to training resources, and yeah, it's going to give you a lot of kind of field experience. Field experience, to be honest, is the best way to learn, right? Is to get out there, and honestly, to see people make mistakes. Hopefully, you don't make the mistakes. Hopefully, you're observing people making the mistakes. But experience is a very good teacher. I will definitely say that. If you can, try to get into some kind of. I would say that the first port of call would be to be in a sales engineer role, if you can, because that's going to give you exposure to the technical side of the business. You're going to have to learn about product line, about different kinds of lubricants, about different kinds of applications. So be very broad. But at the same time, I think I really benefited from time in a little bit of time in sales. I don't personally enjoy it, but what I tend to find is that most engineers are uncomfortable with having frank and difficult conversations with customers, um, and having to have a little bit of sales experience, I think, is actually really beneficial. Now, I've just had a question come through from Peace, who says, how long can the breather last in the lube drum? So I think there you're probably referencing this picture, right, where we had some desiccant breathers on the drum. And unfortunately, I can't give you a definitive answer because how long is a piece of string? Let me give you some ideas of what goes into what can affect a desiccant breather life. So number one would be the size of the breather. So if you can sort of see my hands here, there are breathers that are about this large, if you can see the gap between my fingers. And there are also breathers which are about this large, right? So I would say that one would contain 30 times the desiccant of the other. And they're built for vastly different applications. Some are for tiny, tiny little gearboxes, and some are for fuel tanks, right, which contain up to 100,000 liters of hydrocarbon. So depending on the size, that's going to govern how long they last. Not only that, but the environmental conditions will also greatly affect it. So if you live in a tropical, very humid environment, then the desiccant is going to expire much quicker than if you live in somewhere that's very, very dry. Right. The third factor is how much is the drum in use. Right. So one thing that this will be affected by is how much air is constantly going through the breather. And if you have, for example, a drum that is being effectively used as a day tank, right, and the oil level is constantly going up and down, as in the case of a hydraulic reservoir, then that constant exchange of air in and out of the breather is, again, going to reduce its life. If I were to give some general guidance, right, you want a breather that needs to be replaced roughly once every, let's call it 3 to 6 months, right, in an ideal world. And by the way, that desiccant, it will change color when it becomes saturated with water. And that's when you know that you need to change it. So these orange desiccant breathers, they turn green when they get saturated with water. These blue ones, on the other hand, the blue breathers, they go pink. So that's the indication that you need to change them. Anything else? As we're talking about contamination control, cleanliness, have you got any questions about oil analysis as it relates to machine reliability? Also, something like that? All right, maybe again. Oh, great question. I love this question. Can we consider all new oil to be clean? I love this question. The answer is unfortunately no. Why is that the case? So let's say, for argument's sake, right, that look at it from the perspective of a oil manufacturer, right? And let's say they're making hydraulic oil. That hydraulic oil can be going to a range of different customers. So, for argument's sake, one of them might be in the plastic injection molding business. Plastic injection molders, if you don't know, the servo valves on them are incredibly tight tolerance, right? Because the injection needs to be done with a very high degree of precision. So the tolerances are very small, which means that they need extraordinarily clean oil to function correctly, right? Otherwise, you get product rejections. Versus, you might have a quarry or a mine site, far away from a town center, where they're regularly having hydraulic hoses burst and they're spilling hydraulic oil onto the ground. Those guys would not benefit from clean oil. So, as an oil manufacturer, how clean would you make it? Would you make it for the cleanliness required from a plastic injection molder or from a mining company? So, the reality is, oil companies generally just make oil, they don't clean it to any specific standard, and then the responsibility for cleaning the oil is on the customer, right? To clean it to your own standard. Now, some of the OEMs, right? Some of the OEMs have standards, right? So Caterpillar, for example, I think you need to clean up the oil to an 18, 16, 13. It's your responsibility to do that as it goes into the compartment, right? So that is something that we need to be mindful of. So not all oil is clean. You need to kind of specify how clean it needs to be. Now, another couple of questions: how do we know a clean oil? So I guess that means, how do we measure the cleanliness of the oil? And that relates to the other question, which is, please explain the ISO codes. It's a little bit difficult for me to explain the ISO codes without the table in front of me, but effectively, ISO code is 3 numbers. So let's say, for example, you have 20, 14, 11. What do those numbers refer to? So what they refer to is, the first number is particles greater than 4 micron. The second number is particles greater than 6 micron in size. The last number is particles greater than 14 micron, right? However, it's not the number. So a 20, 14, 11 doesn't mean that there are 20 particles greater than 4 microns. It relates to a size range. So there's actually kind of like a lookup table. So if anyone wants to look for it, it's ISO 4406, right? Is the code that you want to type into Google, and it will bring up a table, and it will say, basically, in a 1 mil sample, if there is a certain range of particles within, then it gets that score. All right, so might be a little bit sort of difficult, but hopefully that explained it. Davis has asked another question: vibration analysis or oil analysis, which is more important in condition monitoring? Woof. Very, very topical question. Okay, which one's more important? They accomplish different things, right? And that seems like a bit of a cop out, but there is an overlap between them. So where does vibration analysis shine? Vibration analysis is going to pick up something like, let's say, bearing dysfunction in, let's say, a damaged roller. You will never identify that in oil analysis. What about imbalance or misalignment, right? You will detect that with vibration analysis. Oil analysis may detect increasing levels of wear as a result of the imbalance, but it won't tell you that there is an imbalance there, right? So that's where vibration analysis really shines, is that in a lot of the mechanical failure modes, it can point to the cause. On the other hand, oil analysis can generally tell you earlier on in the piece when there is wear occurring, and vibration analysis cannot tell you anything about the condition of the oil. So if, right, it is contaminants that are causing the excess wear, then you'll pick that up in oil analysis way before vibration analysis does, if vibration analysis ever does. Right. So which one is more important? I'd say they're almost two completely separate disciplines looking at different failure modes. Sorry, I know that's a bit of a cop out answer, but they do different things. All right. Anything else? Well, that's kind of the end of our time here. Um, if you're interested in learning more, please go over to my YouTube channel, which is called Lubrication Explained. I've got a ton more videos that are over there that help explain different parts of condition monitoring and filtration, engine oils, hydraulic oils, all that kind of stuff. I'll actually be uploading courses there in the near future as well. So, kind of little preview or a teaser of that. Um, so, feel free to reach out as well. There's a link just down below here to the scorecard. If you want to sort of very, very quickly evaluate how you guys are going from a lubricants and reliability perspective. And yeah, just, really appreciate Essa for inviting me on and letting me talk to all you good people.